Hello, and welcome to Part 1 of the TI Precision Labs on op-amp stability. In this video, we will discuss the common causes of op-amp stability issues, as well as how to identify stability issues in the lab using common equipment. The following videos in the series will provide a review of Bode plots, basic stability theory, and how to simulate op-amp stability in SPICE. The remaining videos will address specific compensation techniques with detailed analysis of the solutions. Before proceeding with the op-amp stability series, the lectures and problem sections for op-amp bandwidth 1 through 3 should be completed. The bandwidth video series thoroughly discusses several key concepts used in stability theory that will only briefly be reviewed in the stability video series. Here is an example of what can happen if a circuit stability is not verified before going to production. An op-amp circuit that is unstable will have an unpredictable or unexpected output with poor transient performance. This typically results in large overshoots and ringing when changes occur on the input or load, but may also result in sustained oscillations. Often, stability problems are caused by connecting a capacitor to the output or to the inverting input of the amplifier. This op-amp supply splitter circuit was designed to deliver a constant 2.5 volt DC output for the reference voltage in a system. However, the unstable design resulted in a sustained output oscillation, which has turned the DC reference voltage into a sine wave. Even though this circuit is meant to operate with a DC input and output, transient disturbances on the input, power supplies, or on the output may cause the amplifier to begin to oscillate. Therefore, we recommend checking every op-amp circuit for stability regardless of the closed-loop signal frequency of operation. Too much delay between the amplifier output and the inverting feedback node is a straightforward way to visualize the root cause of op-amp stability issues. The effects of feedback delay are displayed in this example by observing the voltages at the amplifier output, VOPA, and the amplifier inverting input, VFB, when a step is applied to the input, VN. When VN changes, VOPA responds in an effort to set VFB equal to VN to re-establish the virtual short between the inputs. However, the feedback delay results in an erroneous voltage at VOPA by the time VFB equals VN at 0 volts. As a result, VFB continues to rise and overshoots the input voltage, causing VOPA to reverse directions. Depending on the severity of the delay, the output may settle or may result in a sustained oscillation as shown here. While the op-amp circuit with the RC delay elements in the feedback path looks strange and unrealistic, many standard op-amp circuits inadvertently create the same situation when external circuit components interact with non-ideal op-amp properties. For example, an op-amp's open-loop output impedance, RO, frequently interacts with the circuit load capacitance, C load, to form a delay. Another delay is commonly formed when the feedback resistance, RF, interacts with the parallel combination of op-amp input capacitance, Cin, and any stray PCB capacitance. The delay caused by either of these situations can result in stability issues if not properly taken into consideration. So, without further ado, here are the most common circuits and applications involved in op-amp stability circuit issues. These circuits all create unwanted delay from the output to the feedback node and can be divided into two distinct groups based on the issue they cause in the op-amp control loop. The first and most common group of circuits are those that disturb the open-loop gain of the amplifier circuit by presenting a capacitive load either directly or due to parasitic elements on the output of the amplifier. Examples of these circuits include voltage reference buffers, cable shield drive circuits, and MOSFET drive circuits. The second group of circuits disturb the feedback network of the amplifier circuit due to interaction between the input capacitance and large value feedback resistors used in the circuit. Common examples of these circuits include transimpedance amplifiers, circuits designed for low power operation, and circuits that feature transient protection elements on the inverting input. These two circuits are just plain trouble. They will almost always have issues and should generally be avoided. Attempting to filter the signal at the inverting input or output by directly placing a capacitor on those nodes will directly create the two most common causes of op-amp stability issues. These designs are more likely to behave as oscillators as they are to do what was desired of them. If you see either of these circuits being designed, make sure they are thoroughly analyzed for stable operation before taking them to production. Although solving op-amp stability issues takes practice and experience, identifying them in the lab is generally straightforward. An input signal generator and an oscilloscope are all that is required. The input step could come from a DAC that is already in the system or from an external function generator. If they are available, gain phase analyzers and network spectrum analyzers can also be used to help identify stability issues. Here are some images of output signals from unstable circuits taken with common lab oscilloscopes. A circuit with a DC output may look stable when first observed on an oscilloscope until the loop is disturbed when a small signal step or square wave is applied to the input. An unstable circuit's output will overshoot the input signal and will then ring back and forth until the output settles. The magnitude of the overshoot and duration of the ringing directly relate to the severity of the stability issue. Circuits with minor stability issues may feature modest overshoots with minimal ringing. More severe stability issues will result in overshoots equal to or greater than the input signal, with significant ringing as shown in these examples. The most severe stability issues can result in sustained output oscillations without having to apply a signal to the input to disturb the loop. These circuits can produce a wide variety of strange-looking output signals which may not always be pure sine waves as possibly expected. Although not featured here, unstable DC outputs and higher than expected distortion readings can be more subtle signs of a stability issue. In addition to oscilloscopes, gain phase analyzers can be used to measure the frequency response of a circuit, which can also be used to identify stability issues. These results compare a circuit's simulated gain phase response versus the measured response. Gain peaking, rapid phase shifts in the frequency domain, or unexpected gains are all indicators of stability issues. When trying to measure the gain and phase of an unstable circuit, it is common for the measured response to appear jagged or not clean, and may be difficult to measure over the full frequency range. Watch for those more subtle signs of stability as well. The objective of this series is to understand the different op-amp stability compensation techniques, how to select the best method for a given application, and how to design the circuit with optimal component values. As shown, the supply splitter circuit from earlier can be compensated multiple ways depending on the final application requirements, two of which are shown here. This technique uses an isolation resistor, R-ISO, to compensate the circuit at the expense of DC accuracy due to the voltage drop across R-ISO. This technique pulls R-ISO back into the feedback loop, allowing the op-amp to eliminate the voltage drop across R-ISO at the expense of settling time. We'll explore the different methods to stabilize circuits after we review the necessary theory to understand, simulate, and compensate a feedback network. In summary, this video discussed op-amp stability issues, common circuits that cause stability issues, and how to identify stability issues in the lab. Stay tuned for the next videos, which will cover Bode plots, basic stability theory, simulating op-amp stability in SPICE, and common compensation techniques. Thank you for your time. Please try the quiz to check your understanding of this video's content.